Welcome back for another deep dive. You ready to see some things you can't normally see?
You know I am. What are we looking at this time?
Well, today we're going to try to visualize fluid flow.
Interesting. I always thought of that as something you could see. I mean, you can look at a river and you see the water flowing.
Sure, but there's a lot more to it than just what meets the eye, like how fast is it flowing, or in what direction? And what about the little eddies and swirls that you can't really make out just by looking?
Ah, I see you're talking about the details, the stuff we can't see without help.
Exactly, and that's where this amazing technique called Holographic Particle Image Velocimetry comes in. That's HPIV for short, because it's kind of a mouthful.
HPIV, sounds complicated. But hey, that's what these deep dives are for, right?
Right. And we have a great guide for this one, an article by William L. Weaver from January 2002. He traces the evolution of how scientists have tried to capture more and more detail about how fluids move, going from some pretty basic methods to some truly mind-blowing technology.
So, where do we start with this? Back in the Stone Age with, like, cave drawings of rivers or something?
Not quite that far back, but they did start with something surprisingly simple: photography and strobe lights.
Oh, okay. How'd they make that work?
Well, imagine tiny particles suspended in a fluid, and then you illuminate those particles with flashes of light. You can capture those particles in motion on film, and that gives you a glimpse into the flow patterns.
Oh, so like those old photos of like milk splashing or something.
Yeah, kind of like that. But of course, back then it was all done manually. So researchers would have to analyze each photograph by hand and track the movement of every single particle.
Wow, that sounds tedious.
It was. Weaver even mentions a study where researchers spent countless hours drawing tiny arrows on images to represent the velocity of each particle. Talk about dedication.
Yeah, serious props to those folks. But I bet things got a whole lot easier when computers entered the scene.
You bet. The arrival of computers totally revolutionized the field of particle image velocimetry, or PIV. Suddenly, instead of manual tracking, they could use algorithms to analyze images automatically.
Automation. Always a game changer.
Right. One of the key concepts here is autocorrelation.
Autocorrelation?
Yeah. It's like, imagine you take an image of the flow and then compare it to a slightly shifted version of itself. By analyzing how much the image has changed, you can calculate how far the particles have moved in that time.
Oh, okay, I get it. So it's like playing a game of spot the difference, but with science.
Exactly. And that automation meant scientists could analyze way more data in a fraction of the time. But even with these advancements, there were still some limitations. Like, early PIV techniques were mostly limited to 2 dimensions.
2 dimensions. So they could only see a flat slice of the flow.
Yep. Like, imagine looking at a flat snapshot of a complex, swirling flow. You're only getting a tiny piece of the picture.
Ah, I see. So how'd they figure out how to see the flow in 3D?
Well, they had to get creative.
Oh, I like where this is going. Tell me more.
Okay, so one approach they came up with was to use 2 different colors of light to illuminate the particles. Imagine like tiny color-coded tracers flowing along with the fluid.
Okay.
And by analyzing how the colors shifted over time, they could get a much clearer picture of the flow's direction.
Ah, that's pretty clever, like giving depth perception to their measurements.
Exactly.
Yeah.
And then there was stereoscopic PIV. It's like using 2 cameras to view the flow from slightly different angles, kind of like how our eyes work.
So by combining the views from the 2 cameras, they could reconstruct the flow in 3D.
Yep. They were basically giving the measurement a sense of depth and volume. But, you know, scientists always want to push the boundaries, right? They wanted to see even more detail.
Of course. So what happened next?
That's when things get really wild, because that's when holography comes in.
Holography, finally. Holography. Now we're talking. So how does that work for fluid flow?
We'll get this. Instead of capturing just a 2D slice, imagine being able to freeze the entire flow, like a 3D snapshot. That's what holographic PIV, or HPIV, can do.
Wait, seriously, a 3D snapshot of the entire flow? That's insane.
It's pretty mind-blowing. But I gotta ask, how does holography even work? I mean, I know it makes 3D images, but isn't that like Star Wars stuff?
Well, it might seem like science fiction, but it's definitely real science. It's all about light and how it interacts with the particles in the fluid. See, with holography, you're not just capturing an image, you're actually recording the interference patterns that are created by laser light as it bounces off those tiny particles. It's like creating a unique fingerprint of the light field.
Okay, so it's like capturing the light waves themselves.
Exactly. And those interference patterns are recorded on a holographic plate. And from that plate, you can actually reconstruct the entire 3D flow field.
So it's like having a 3D model of the flow that you can explore from any angle.
Exactly. Pretty neat, huh?
That's incredible.
And here's the really cool part. We've been talking about using these particles to visualize the flow, but what we're really seeing is the movement of energy.
Whoa, hold on. The movement of energy.
Yeah. It's not just about tracking the particles themselves, it's about understanding how energy is flowing and dissipating within that fluid.
So it's like we're seeing a deeper level of what's happening in the flow. It's not just about those particles, it's about what's
Yeah.
driving them.
Exactly. And that opens up a whole new way of thinking about fluid dynamics. Like, imagine being able to visualize the turbulent flow of air over an airplane wing in super detail. We could see exactly where energy is being wasted due to drag
Right.
and use that information to design much more efficient airplanes.
Oh, wow. So it's not just cool visuals, it's actionable information.
Exactly. And Weaver was already hinting at some of these possibilities back in 2002.
That's wild.
Yeah.
So what do you think HPIV is capable of today that Weaver might not have even dreamed of?
Ooh, now that's a fun question. You know those holographic projections you see in sci-fi movies? Well, think about this. The way HPIV captures dynamic 3D data could be the key to making those projections even more realistic. Imagine seeing a swirling vortex of air currents rendered in holographic form right in front of you.
Whoa, that would be amazing.
It would. And that's what makes this field so exciting. The lines between science fiction and reality are blurring more and more every day. It's really a thrilling time to be exploring the world of fluid dynamics.
It's amazing to think how far we've come from those early photos to like holographic projections of an entire flow.
Yeah, it is. And it all started with just wanting to see a little more detail,
Yeah.
Then all of a sudden we're like, whoa, we can see energy moving around.
And that was one of the things that struck me in Weaver's article.
Yeah.
He mentioned how HPIV can generate huge amounts of data.
Yeah.
And just making sense of all that information can be a challenge in itself.
Oh, yeah. It's like you can have all the data in the world, but if you don't know what to do with it, it's just noise.
So how do we move forward from there? How do we unlock the full potential of all this, amazing technology?
Well, one thing that's becoming really important is artificial intelligence. Like, imagine algorithms that can go through all that data, all those terabytes, and pick out patterns and stuff that we humans would just never see.
So it's like we're teaching computers to see the world through the eyes of fluid dynamics.
Exactly. It's like giving them a whole new way to understand the world. And who knows what they'll discover? Maybe they'll even help us finally understand turbulence, which is one of the biggest mysteries in physics.
Turbulence. Yeah, that's one of those things that's always sounded, I don't know, kind of intimidating, like way too complicated for me to even think about.
Oh, it is complicated. But that's what makes it so interesting. And if we can figure out how to predict and control turbulence, it would be huge. I mean, think about weather forecasting, designing better engines, you name it.
Wow. Yeah, that would be incredible.
And think about medicine. Like, imagine using HPIV to study blood flow in the body. We could maybe diagnose heart problems way earlier or figure out how to deliver medications more effectively.
Yeah. Or even like visualize the flow of cerebrospinal fluid in the brain, which could help us understand all sorts of neurological conditions.
Exactly. The possibilities are really endless. And it's not just about HPIV, it's about this whole journey of discovery, like how we went from these simple methods to this incredibly sophisticated technology, and we're still learning so much. It shows you how much potential there is out there, you know? How many things we don't know yet.
It's like we're just scratching the surface of what's possible.
Yeah, and it's all driven by this like fundamental human curiosity, this desire to understand the world around us. And that's what I find so inspiring about it.
Yeah. Well, I have to say, I'm definitely feeling inspired now, and I hope our listeners are too. So next time you see like a plume of smoke or a river flowing, take a moment to think about all the amazing stuff that's happening that you can't see. All those intricate patterns and forces that shape our world.
It's like a whole hidden universe right there in front of us.
Exactly. Well, thanks for joining us for another deep dive. We'll see you next time.